Good morning. So, how are you all? Today we are going to study alkenes part 2. Preparations is our concern topic. Yesterday we started elimination revision and we completed even elimination reactions. Yesterday I also referred, today I'm also telling again that eliminations are quite confusing to substitution. So, wherever I can, I'll always compare them with substitutions. Like yesterday, we compared E1 versus SN1. Today, we will compare E2 versus SN2 and we'll also study EI and even CB. So, let's start with our work. Today, as I said, we have to start E2 reactions. Yesterday, we saw that an alpha beta elimination reaction, alpha beta elimination, or simply beta elimination reactions are classified into following four categories: E1, E2, EI or EC, and even CB. Correct? So, E1 we did yesterday. Let's start with E2 today. So, what is E2 reaction all about? Well, E2 reactions, their full name is they are called bimolecular elimination reaction. They are bimolecular elimination reactions, and this particular E2 is a single step reaction. As yesterday we were talking that E1 will involve minimum of two steps: formation of carbocation and then removal of alpha H of that carbocation. But today it is going to be a single step process. They'll proceed through transition states only. So now how does this E2 happen? To understand this E2, let me exemplify my whole set of working with some alkyl halide. Say, for example, we are having this alkyl halide and are considering its reaction with alcoholic KOH. Then how the reaction will proceed. Let us exemplify our whole E2 with respect to this particular molecule. And here, please consider in my primary talks these halogen as XCl and uh, X as Cl, Br, and I. In the end, I'll talk about what if it was fluorine. Okay, default consideration, please take default as chlorine, bromine, and iodine. So let us start. It is a single step reaction. If I want to talk about the confirmation about this particular, okay, and what are the possibilities? So, if I talk about the conformation of the leaving groups on this particular bond, that is C2C3 bond, if I say my halogen is placed here, okay, then here is CH3 and H, this is carbon number 2. Carbon number 3, if the H I want to remove, I'll mark it with this, is like this star, and this CH3. So this you can say that this is a syn periplanar conformation. Okay. There is another possibility that X, H, CH3, H, CH3, and H, it could arrange like this. Okay. This is called anti-periplanar conformation. Anti-periplanar conformation. Just keep these two things in mind. And now let me start the mechanism. As I told, it is a single step reaction, so it always proceeds with concerted mechanism. The word concerted implies simultaneous bond fission and formation. Concerted implies simultaneous bond fission and formation. Now, if I want to write the possible mechanisms or possible transition states for this molecule when a strong base like alcoholic KOH or NNH2 attacks. Okay. Now there could be two cases. What two cases? First, I'm talking about regio. Then I'll be talking about stereo. So there could be two cases. If I talk about regio, this base can attack here. Okay. Let me draw it here clearly. So CH3, CH, this bond will start breaking. Base will start forming bond with this beta H. Here a new pi bond has begun, del minus CH3. Okay, so what I have drawn? I have drawn ZZIF anti-periplanar, ZZIF anti-periplanar transition state. Okay, this is called ZZIF because the transition state is having the alkene towards more substituted carbon. I can have the similar if I have del minus CH2H base del minus like this. This I will call it as Hoffman anti-periplanar transition state. Okay. Could there be syn periplanar transition state? Yes, possible. Why not? We can draw. Whether it happens or not, that you decide. I'll give you a hint. Just let me complete the transition state. This I can call as ZZIF syn periplanar transition state. These all are possible transition states. CH3, CH2, CHX, CH2, H base del minus. This is Hoffman syn periplanar transition state. This is Hoffman syn periplanar transition state. Okay, as and when they all complete, when these transition states proceed to final products, my choices would definitely be formation of 2-butene in my given example and formation of 1-butene. Okay, these are my possible choices. When X is Cl, Br, I and base is non-bulky, then major product is ZZF product. Non-bulky like alcoholic KOH, like NaNH2, etc. When X is F, then always Hoffman, major product. When X is Cl, Br and I and base is tertiary butoxide or any bulky, then this is major product. This is one thing, that with X equal to Cl, Br and I, only with bulky base we can have Hoffman products. But when X is fluorine, then always we have Hoffman products. Now, what is the reason? That I'll tell you, that why and when these are the major products, how it proceeds. Okay, first let us see here, just revise once, that these were our TS. A base approached, a more substituted hydrogen was approached. It could be from the same sites in periplanar or it could be from anti-periplanar. Certainly, anti-periplanar will be the most preferred as it is having the distance possible farthest between the del negative centers in the transition state. In sen periplanar, they are relatively closer. Okay, so why this uh, anti-periplanar and ZZF1 is usually major? Okay, this is major usually. This is the preferred. And when others will come, that we have seen slightly here. Okay, please take this as a important note that these are when Hoffman are formed. To understand why ZZF and antiperiplanar transition state is major, we need to know a postulate, a theory called Hammond postulate. Hammond said that transition states cannot be isolated, cannot be studied. What are transition state? There is a difference between intermediate and transition state. If in a reaction I am drawing this, then this is my TS, this is my intermediate. This is my TS2. This could be product, this could be next intermediate 2, and so on. So this top peak are the transition states. Now transition states you cannot find. They cannot be isolated, they cannot be studied as free species. We don't know what will be their charges, how will it behave, and all those things. Okay, so we don't know all those things, but Hammond said that a transition state will behave. Please listen carefully. Transition state will behave like the one in a reaction, either reactant or product, with which it shares less energy difference. Okay, like in an energy curve, transition state is at a peak, so definitely it is having some energy difference with reactant, it is having some energy difference with product. If the step is endothermic, then certainly the transition state is having less energy difference with product. If the reaction would have been exothermic, then its energy difference, let me draw a step. If it was exothermic, the step was exothermic, then it would have been like this, na? Please maintain this side is as usual energy and this side is the reaction coordinate, the time with which the reaction is proceeding. Same way here. So from here you can see that the transition state is having a lesser energy gap with reactant as compared to product in exothermic. In endothermic, it is having lesser energy gap with the product rather than the reactant. Okay, so Hammond said that TS will behave like a reactant or product side in the energy diagram with which it shares lesser energy gap, with which it shares lesser energy gap. That side it will behave. Okay, so in an endothermic, that is elimination as is an endothermic, I can say that my transition state will behave like products. If I draw the energy diagram for E2 reaction, in case of E2 reaction, my energy diagram is a single step and it is an endothermic reaction. So here is my transition state. Here is my alkenes. Here is my, as I have exemplified with alkyl halide. Okay, here is the reaction growth. And here we are having energy. Okay, so if you see that alkyl halide goes to transition state and then transition state to alkene. So E2 TS behaves like alkenes. What do we do with if it behaves like alkene? Well, once we find out that it behaves like which reactant or a product, then what we do? Then a clarity comes that this transition state stability will be influenced, will be affected by the similar factors with which it is resembling. So E2 transition state as is closer to alkenes in energy, then certainly the transition state will be stabilized by all those factors which will stabilize the alkene. Okay, so TS will be stabilized by factors influencing alkene stability. This is fixed, that it will be stabilized by the factors which will affect the alkene stability. So if that is so, okay, alkene is stabilized by hyperconjugation. Alkene is stabilized by resonance, steric, and so on. Con- this particular fact, once is cleared in our concepts, I think you will be easily accepting the fact that normal E2 is going to be anti-periplanar Sedezef alkene formation. This is what it should be mainly, this is what it should be majorly, because as I have explained, the transition state which involves the removal of H in a way that a more substituted alkene is formed will give the more stable alkene. Okay, from here itself I can say that bridge head will not acquire planarity. So what does that mean? Doesn't acquire, तो हमें क्या करना? Well, let me try. See, for example, if I have halogen over here, okay, if I have halogen over here, I will never have a product, whatever the substitution factor might support. That here it is more hyperconjugative and all that. But as I said, don't go by the conclusion, go by the basic. That will this transition state be able to exist? No, never. So this will not be formed. Okay, so what will be formed? We will have a product. As Anaki, we will have a failed reaction. This is what will be formed. Alkene will be formed from here. Okay, so somehow we had some product, but if the same reaction would have been, say, like this, and now I introduced base and see what would be the product. There is no choice, whichever side I go, something like this or something like this. But in all possibilities, this is a big no no. Okay, E2 fails here. No possibility. And the reason you can easily understand through Hammond postulate that these structures are not possible. Though with the increase in the ring size, there is a possibility that a bridgehead may acquire planarity. Okay, but that depends, that is relatively on much larger rings. I would say that the allowed bridgehead types are somewhat like this type. When you have a big or a large ring, then these things could be possible. Okay, so normally what we have concluded that it is going to be set ZEF, regioselectivity also we have discussed, and it is going to be anti-periplanar elimination reaction. We already know that eliminations are endothermic, so high temperatures will support E2. Okay. Now, keeping this E2 is anti-periplanar in mind, if we have a specific type of reactant, what would be the product? That we'll discuss after some time. Okay, so let us proceed. So point number 2, rate of E2 will depend on strength and concentration of base. Okay, you need to have a strong base and you need to have a high concentration because the rate of E2 is alkyl halide into base. Both are involved. Okay, in the RDS, it is a single step. Both are involved. So for a good reaction, you need to increase the base concentration. You need to increase the base strength. Number third, rate of E2 directly proportional to leaving group nature of X. As soon as it goes, as fast as it goes, rate of E2 will definitely improve. As in the RDS, we have a bond breaking of carbon and halogen. Okay. Point number 4, with increase in stability of alkene formed, rate of E2 will increase. As we have just discussed, Hammond postulate, as and as the alkene form will become more and more stable, E2 certainly will become better and better, faster, as well as the yield will improve. Okay, rearrangements are totally absent. Rearrangement are absent because there is no carbocation form, nothing such intermediate is involved, so there are no rearrangement in E2 reaction. Okay, till here I hope it is clear. Now, as I was telling, a little more stereo I will discuss of E2 reactions. So let me try and to explain certain points of E2 reactions with respect to its stereo. Okay, with respect to its stereo. Now, what I want to say, let us consider that I have a molecule CH3H bromine, okay, H and say CH3 and C2H5. Let us consider this is the Fischer representation I have drawn, that I have this molecule. Then I have another diastereomer of this molecule, C2H5, correct? Bromine, H, H, CH3. Now, if E2 reaction happens, what would be the products formed? Okay, what would be the products formed? For such questions, please make it a rule that convert them to either Sahars or Newman. And the second point, whenever you convert Fischer to Sahars or Newman, Fischers are always, okay, always are eclipsed conformations. So this will be converted to its eclipsed conformation. So first I am taking case 1. Okay, so the way it is given, I will say that it is CH3, C2H5, bromine, CH3, H and H. To have the anti-periplanar arrangements, I have to rotate it to say bromine, H, CH3. This H has to go down, so CH3 and C2H5. Okay, now we attack base. Now when base attacks, this is how this elimination will take place. There will be certainly transition state. In my transition state, as I have said, that alkene character begins. Okay, there will be formation of this Br del minus, this bond base del minus, Me, Et, H and CH3. This bond is breaking, forming and breaking. Sorry, forming and breaking. So when this completes, I will have H, CH3, Me, and Et as my final products. Okay, I hope it is clear. Now, coming to case 2. Coming to case 2. First, let me draw the Sahar's conformation of case 2. So it is Me, Et, Et, H, CH3, bromine, and H. This is what is there. Okay. Again, same thing. Rotate to antiperiplanar. Here is my bromine, Me, H, H, Me, Et. Again, base attacks, same way transition state is formed, and the product will be, when I'll remove this, I will have Me, H, Me, and Et. Okay, so how to do these questions, how to eliminate, this is the way. This is the standard way. You can see we are having two different geometrical isomers, if I could name them. Here it is E isomer, this is a Z isomer. So if I'm starting from one particular type of optical isomerism, I'm ending to a particular type of stereoisomer of GI. And this is what is called stereospecificity and stereoselectivity. So E2 reactions are certainly very stereospecific and stereoselective. It is not that all will be formed always as a major product. Okay. Now, as we have seen, I want to tell a shorthand. If you like, you can use it, or else you can go by the standard method that I have just discussed. A shorthand I use is if the two groups which are being eliminated into antiperiplanar arrangement are both on horizontal. Okay, if the two groups which are to be eliminated from an antiperiplanar arrangement are both on horizontal lines of the fissure, then just remove them, draw the alkene that would come in a 2D without a second thought. But for answer, revert it. Revert it. So, for reporting an answer, you have to report this one. Okay. Similarly here, no need for across or same side. That has same effect. Me, H, double bond, Et, Me. This is what you got when first you have just removed and drawn. Now for answer, I have to revert it. So I will write it as Me, Me, Et, and H. And see, by the complete technical method also, you got the same products. So you can use this shorthand in case of fissures. The two groups which you are eliminating in E2, if E2 is antiperiplanar, then once you remove them, draw the alkene by 2D approach, and please report your answer as opposite of alkene that you have got. There are reasons why this is true and all, but you can use it directly as a shorthand. Now a question may come, what if one group is on vertical and other is on horizontal? Okay, one is on vertical, other is on horizontal. Then what we have to do, then just remove those group and draw the alkene, and that alkene itself is your answer. Then no need to revert. You have to revert only when both the groups are either on horizontal or both the groups are either on vertical. Okay, but one vertical, one horizontal combination, if is there, no need to revert your answer, just report directly. Is that okay? So, as I have continuously using it as NT, is it that all the E2 in the world are NT? Well, not really. It is the preferred mechanism. It is something that, given a choice, molecule will prefer. But certainly not the only case. In case of cyclohexane, though, which is most important for our syllabus, this is certainly the most common method. Okay, if I talk about cyclohexanes, this certainly is the most common method, but this is the only method. If I say, then it is wrong. Okay, if I say this is the only method, then it is wrong. There are in fact possibilities that the reactions E2 reactions may have proceeded through syn periplanar eliminations. Okay, can they have syn? Yes, there is a possibility. But that is only when NT is failed somehow. Okay, sin is found only when NT is failed. And second observation is rate and yield both go down. बहुत ही कम हो जाती है, बहुत negligible हो जाती है. In case of cycloalkanes, certainly ring size decides whether sin elimination is even feasible or not. If ever happens, percentage sin elimination if ever takes place. So let me tell you, when you talk about cyclobutyl rings, it is 90%. When you talk about cyclopentyl, it may go up to 46. Just as I told, in cyclohexyl, it is almost negligible. It is only 4%. Okay, in case of cycloheptyl rings, it is again coming back to 37 percentage. Is it okay? Now this particular that cyclohexyl rings totally go for anti-eliminations, so stereo selective about their anti-eliminations, or else they do not react. Okay, there's such a strict preference of cyclohexyl groups for anti-eliminations has been observed in C6H6Cl6 isomers. Okay, as we know that C6H6Cl6 isomers have total 9 stereoisomers, including stereoisomers. It has 9 isomers, out of which 8 are geometrical and one pair will behave as optically active. So it is 9. Okay. Now when we put this particular uh, 9 isomers in on reaction with alcoholic KOH, strong base, okay, then the variation in rate is 7 to 24 into 10 power 3. Okay, its rate varies from 7 into 10 power 3 to 24 into 10 power 3. Uh, if that is so, almost all are reacting. But one particular which is found that it do not react. If there is one particular which do not react at all, it is this one, in which all our chlorines are equatorial. When all our chlorines are equatorial like this particular isomer cannot acquire all axial geometry. And so E2 totally fails for this. This total study of C6H6Cl6 E2 reaction has cleared the air that E2 of cyclohexanes strictly follow anti-periplanar geometry, or else it would rather fail for E2 reaction. But in other possibility, certainly syn or nt could be there with nt being major. Okay. As far as J is concerned, if you have to make a choice between syn and nt, go for always nt. And if for whatsoever reaction you find that nt is not happening in cyclohexyl or in usual molecules, then as per options, you may even go for no reaction. Okay, if that comes, though they frame the question experimentally, so they will all be evident, but you for J, you strictly stick yourself to anti-periplanar eliminations. Correct? Now let us discuss why regiochemistry of E2 reaction varies. Okay, we have cleared that. Okay, we'll go to anti-periplanar geometry, anti-periplanar conformation for E2 to happen. But then also, why sometimes ZZEF and sometimes Hoffman products are formed. So let me tell you the reason for that. Now see, when the mechanism is perfectly concerted, that is, the time lapse between the bond fission of CH and CX is almost zero. They undergo the bond fission parallelly and the reaction is totally concerted. Okay. Then in the transition, there is no carbanic character, no carbocatanic character. It simply behaves like an alkene. And so ZZEF remain as the preferred product. So ZZEF remains the major or the preferred products. But if whatsoever the reasons may be, okay, anyways, if instead of this X del minus CH2 H base, okay, but if this base becomes very bulky. Now see, if that base becomes bulky, it is easier for this base to approach less substituted carbon H rather than more substituted carbon H. Why? Due to steric factors. Okay, please consider this base. Let me exemplify with tertiary butoxide. O minus certainly is a very small, O minus is small, but as soon as we go to tertiary butoxide, the back bulky portion of the base has suddenly increased. O minus is a second group atom, no problem. It looks more like something, an English woman gown. An English woman gown, like here, it is small. But as soon as it goes down, the whole diameter of the dress increases. So is our tertiary butoxide. So even if it wants to go to this side, okay, you can imagine that even if it wants to go, these portions will be sterically hindered by other substance surrounding that edge. Okay, so yes, still, ZZEF alkene is more stable, no doubt. Our base, if could have, would prefer the ZZEF alkene again. But if there is the probability of ZZEF transition state formation has decreased due to its own steric factors, then due to no choice condition, answers shift towards Hoffman alkenes. So in the top, in the net reaction, we have written that if the halogen is chlorine, bromine, and iodine, that with alcoholic KOH, that is small base, when it has equal ease to approach substituted and non-substituted H, answers are ZZEF. But if I have a bulky base, when my ease of approach to those two H is not same, is not identical, then the answers are shifting towards Hoffman. So the one condition in which answers are shifting to Hoffman is the use of bulky base. Condition number two. Condition number two, if mechanism is not perfectly concerted. What does that mean? That the time in which the carbon hydrogen and the carbon halogen bond break is not exactly same. Okay, is not exactly same. Now there could be two possibilities. I'm not saying that it straight away breaks, but there is a very slight gap. Okay, so what are the possibilities? If CX bond breaks much before CH bond, then it is even. Carbocation will be formed and reaction will go by even. If CH bond breaks much before CX, then it is even CB. Because full anion is formed and it is called elimination through conjugate base. Okay. If CH bond breaks slightly before CX bond, okay, CX bond mechanism is still mechanism is still E2. No carbon ion is formed. No carbon ion is formed. But the transition state acquired carbanionic character. Full carbon ion is not formed, but if the CH bond is having a lesser time requirement for the bond breakage as compared to CX, then a del negative character will be generated on the TS. If this type of del negative character will be generated, see, this is going, a del negative character generates here or del negative character generates here. Certainly, less substituted will have more stable anion. So, this side it will be more stable, and as a result, okay, Hoffman products are major products. Then, Hoffman products are major products. Okay, whenever this happens, then answer shifts towards Hoffman products. This particularly is the case when this X, or I can say the leaving group, is some positively charged species, say like SME2 plus, or it is NR3 plus, or I can still say fluorine. Fluorine itself, bond energy being higher, will go by slower rate and its inductive will generate slight acidity in the beta H. Okay, so overall answers become E2. Oh, sorry, Hoffman E2. If I could exemplify in place of this CH3, CH, X, CH2, CH3, and we take the reaction by same base, let me write if this X is so, and then percentage of 1 in and 2 in percentage. If X is bromine and you use alcoholic KOH type small base, then this is 19% and this is 81 percentage. If it is SME2 plus, then this is 74 percentage, this is 26. If it is NME3 plus, then this is 95 percentage and this is just 5 percentage. Okay, so as and as it is becoming more and more minus I, electron withdrawing, Answers are shifting towards Hoffman products. Okay, so this was dehydrohalogenation of alkyl halides to alkenes using alcoholic KOH. Okay, can we have alkynes also by this method? Yes, you can. Alcoholic KOH, CH3, CH double one, X, CH3. This is our first step. Now for next step, you have to remove this vinylic H. So for second step, I would prefer NaNH2 because NH2 minus is a stronger base than alcoholic KOH. Then my answers will be alkyne formation. Okay, so only when we have a stronger base, then we can have alkyne formations. Otherwise, my reaction might stop. Okay, otherwise, my reaction might stop at alkene stage. Is that clear? Can we use NNH2 in this step? Yes, whichever is stronger base can be used in place of weaker base. Stronger can as be replaced by weaker. Okay. So it depends on the reagent. I cannot say that both of them will have the same reagent because for E2 reactions to happen, I need strong base. Okay. But for E1, weaker base are usually present. Till here it is clear. When does it happen? E2. And yes, from alkenes to alkynes also the reaction shows very specific behavior. Very specific behavior towards its anti-stereoselectivity. Like what do I want to say? For example, I have C X double one C HCH3 and now I put it to NNH2. So my answers will be this. But if, just imagine, if it is this, then it forms alene first. It won't have elimination from this side. It will have alene. Yes, alene rearranges to alkyne is a different thing. But the pathway, but the pathway is through alene. It is not directly to alkynes. And the reason, if someone asks, then please tell that it is NT and the NT conditions are not achieved in this given isomer. That is why it has been through alene, then alkyne. But NT is compulsorily maintained. Okay. So what are other examples of E2 reactions? Well, other examples of E2 reactions, first I'll say is dehalogenation. Dehalogenation of vicinal dihalides is also an example of E2 reactions. It can be achieved by metals. But here I am considering particularly if I have vicinal dibromides like this and we use reagent NaI in acetone, something like Finkelstein, then we can have alkenes. Now this mechanism is also E2. And how it proceeds? It proceeds somewhat like bromine, bromine, I minus, it attacks into the empty orbital of this Br and the transition state like E2 is obtained, Br, iodine del minus, C, Br del minus. Is it okay? Please observe it. If you have any problem, you can post in our Facebook page. If I could, I will surely like to answer. Okay, so you can post it there. So I said This is how it will attack. Now, when this bond is being formed, this is broken, this is formed, this is broken. Till here it is okay. This will again form alkene. What are the other products that are obtained is IBr. There is certainly in the medium extra I minus, and Br minus is formed here itself. Correct? This I minus takes away this and it forms I2. Br minus is liberated. One Br minus was already there, one more is liberated, and I2 is formed. Okay, so this is how dehalogenation by the usual methods and NiAcetone can also be achieved. Another example which I did not mention is pyrolysis of quaternary ammonium hydroxides. This is also a method. It is E2 and always answers are Hoffman. Okay, quaternary ammonium hydroxides. So what we'll do is we'll take a primary amine if I take as a starting point. I'll convert it to quaternary ammonium salt. So by reacting it with 3-MEI, I will have this type of quaternary ammonium iodide. Now I'll treat it with Ag2 aqueous so that this AgI is removed and instead we have quaternary ammonium hydroxide. Why we did this? Because hydroxide is a stronger base. If I'll heat it, this base can cause elimination. But I negative was a poor base. It could not do my purpose. So once I have reached this, now NMe3 plus OH minus is in the medium and we are heating. So when I heat this, then always how you will proceed, I want to tell you that. Nitrogen से connected H always mark it as alpha and further H you mark beta. In all E2s you can do this. Leaving groups attach carbon you mark alpha and the next ones you mark beta. Remove H from beta and alpha say this. Though there is a complete E2 everything goes on, but for a net reaction I want you to do this. CH2 double bond CH2 plus NMe3 3 degree amine. Okay, so you have to remove H from beta and alpha say NMe3. What if my nitrogen had different possibilities? Okay, CH2, CH, H, CH3 and so on. Okay, Me, CH3 plus YOH minus heat. So for this, when you have more choices, please mark them as alpha 1, alpha 2, beta 1, beta 2. If there were more, you could have marked further, you could have marked more. As many there are, please mark them like that. And once you mark all these, now you see which beta H is least substituted. If I remove this, I have one substitution of CH3I. Correct. But if I'll remove this, I have no substitution of beta H. Is that okay? So once I identify this, I will prefer this removal because it goes Hoffman, it removes, it will have a carbanionic character. Carbanionic character here will be more stable. So this plus Me and MeCH2, CH2, CH3. So where you have to form an alkene, the side from which it is least substituted. Yes, if you come across that from both betas, the substitution is similar. If you come across like that, then the second thought is the one which is more hypoconjugative, alkene is formed. But first is the carbanionic character. Okay, so it is Hoffman, it is E2, pyrolysis of quaternary ammonium hydroxide. Next, we move to something called EI or EC. EI or EC is a cyclic elimination. EI or EC, EI or EC is cyclic elimination. There aren't many examples for this. We have only, to be in syllabus if I talk, only pyrolysis of ester. Okay, the fixed particular points for EI and EC fix. It is always going to be pericyclic. That is, it will proceed through cyclic transition states. Pericyclic means reactions which proceed through cyclic transition states are called pericyclic. It could be 5-membered, okay, or it could be 6-membered transition state, but it has to proceed through transition state. That is first. Okay. Second is it always form Hoffman products. Rearrangement not possible. Rearrangement will be absent. Point number 4. As a rule, always give Hoffman products. Oh, sorry, we have already written. So it is a syn elimination reaction. Syn elimination reaction. Okay, these are the 4 points that are compulsorily there. As for syllabus, first only, but sometimes Cope's elimination is also needed. Cope's elimination is pyrolysis of quaternary ammonium, tertiary amine oxides. Pyrolysis of tertiary amine oxides. So first we are having pyrolysis of ester. If you have ester, then always remember pyrolysis is of the alcoholic part from the ester. Alcoholic part of ester. Always remember this. Not from the acid part of ester. It is always from alcoholic part of ester. It is a single step. You just have to heat it strongly and it proceeds. Just heat strongly and a transition state will begin to form. Okay, bond break, form, break, form, break, and form. Okay, so here is a 6-membered TS. Now you can see in this TS formation itself, with respect to this new coming bond here, the 2 leaving groups are on the same side. They have to be from the same side. This elimination has to be from syn periplanar conformation. Then only it can take place, like this cycle formation can take place. Okay, otherwise not possible. So it is a syn periplanar elimination. And it will always attract the H, which is more acidic. So it is always Hoffman. And see, when it completes, we will have CH3, COH double bond O plus CH2 double bond CH2. So what are the important points? You have to remove syn periplanar H. You have to form Hoffman alkenes compulsorily. And the alkene is from the alcoholic part of ester, never the acidic part of the ester. That is also An important point. Okay. They do have kinetic isotope effect because if this H is removed to is exchanged to deuterium, rate of reaction will certainly go down. Second is Cope's elimination. Now, Cope's elimination, as I said, is a pyrolysis of 3-degree amine oxides. So, what if I have a 3-degree amine, say like this? I treat it with some peroxy acid, this or CF3CO3H. Then I will have a tertiary amine oxide. A coordinate will form from nitrogen to oxygen. If I heat this tertiary amine oxides, let us draw the transition states. Okay, if I heat this, see nitrogen, Me plus CH2, CH2. Okay, here there is oxygen minus and here there is beta H. So again, if you see, this is alpha, this is beta. Again, you have to find the most acidic H. This negative will attract H and a 5-member transition state is formed. Here we will have CH2 bond formation, H bond breakage, okay, nitrogen, Me and Me, this will become del plus क्योंकि bond break हो रहा है. Oxygen, this bond is forming, this is becoming del minus. So there is a 5-membered syn and Hoffman TS. When it will complete, we will have CH2 del 1 CH2. Here is certainly CH2 plus dialkyl hydroxylamine. The other product is dialkyl hydroxylamine, Me2NOH. Is that clear? It is Me2NH and OH. So that brings us closer to EI or EC. Now we are coming to our third of the day and fourth of the total beta elimination class, that is E1CB. E1CB is unimolecular elimination through conjugate base. It is a unimolecular elimination through conjugate base. I can see or I can say that it is just an extreme version of the Hoffman elimination in E2. Okay, it is just an extreme version of Hoffman elimination in case of E2. Now, how can I say that? What am I saying? It is an extreme version of Hoffman elimination of E2. See, in our transition state, we were talking that if the transition state acquired carbanionic character, but what if a complete carbanion is formed? So, for this to happen, let me write a general mechanism that there is a H, there is a leaving group. When a strong base comes, a complete carbanion will be formed. No fixation to anti-elimination this time because a complete carbanion which can undergo flipping is formed. Okay. So, and then this goes to removal of L. As the first step is highly reversible, this is RDS. First step is highly reversible as the carbon set HH is very, very, very bad acid. Okay, so second step will act as a RDS. If I take second step as a RDS, my Rate equation will be rate constant into concentration of conjugate base. Okay, rate constant I can say of second step, I can say of first step. So second step. But I want conjugate base to be written in terms of initial reactant. So I'll say its concentration is K1 into RL into base. Now these two together will generate some new constant. So this is so close rate. It is a unimolecular, but is a second order reaction. Okay, this is same as E2 rate equation. So by simple kinetics measurement, I cannot say whether the reaction is even CP or the reaction is E2. Okay, is E2 Hoffman or is even CP? It is difficult to clarify. The only way to say is use of D2O in reaction condition. Use of D2O in reaction condition. So what will happen if I use D2O in reaction condition? The conjugate base which is formed, okay, it is reversible, na? It can absorb D2O, it can have H2O if you add. So if you find exchange of this beta H to deuterium, if this is observed, then it is E1CB. A full carbon ion was formed. If this DH exchange not found at all, then it is E2 Hoffman. That is how we conclude whether the reaction is E2 Hoffman or is E1CB. There are not many possibilities for a reaction to be E1CB. There are very rare possibilities because first the acidity and second then the removal of that particular group. So it is not common. But if it is found, then what? So it is found in compounds where you have lot of electron withdrawing groups like this. Okay, it is this if you introduced base, certainly of possibility of full carbon ion. One fluorine itself was causing carbanionic character. So lot of fluorine will together cause full carbon ion. So here we have double bond like this. Okay, is it okay? So when you have such strong electron withdrawing group, then there is a possibility. Normally, basically, E2 is more favorable by approximately 30 to 60 kilojoules per mole. Formation of this anion is very difficult, and then removal of this bad leaving group fluorine. So if any way fluorine count is decreased, it shifts back to E2. Okay, it shifts back to E2. Second condition is dehydration of aldol. If I have something like this, now you treat it with concentrated base, we'll have an ion. Now removal of this OH, which is a bad leaving group, is difficult. So RDS is this again. So dehydration of aldol under basic conditions is even CB. Okay. From this I can say in general, whenever I have CH3CO, CH2, CH2L And this L is a very bad leaving group. This L could be PHSE, PHO, PHS, say CN, etc. Okay, then they are always even CB. Then the reaction shifts to even CB. Okay, and you can have so many questions. You can replace this by nitro, by cyano, etc., and can frame a similar compound. Though I would always suggest have an experimental backup of whatever you say, because there could be a marginal line between even CB and E2 Huffman. So it is always preferred to go by specific observations and specific results rather than randomly saying that this reaction is going to be even CB. Third is reverse of cyanohydrin formation. That is also even CB. Okay, that is also even CB reaction. RCOHHCN. When we introduce OH minus, first conjugate base O minus is formed, and then it loses this. Okay, aldehyde is formed like this. So this is also even CB. This is the RDS. Okay. One point I would like to add in a conclusive note, that if you have a choice of PHCH2, CHX, CH3, CH2, CH2, CH3, whether this reaction would have been set as if or Hoffman, whatever the conditions is. Once a double bond possibility with pH comes, then irrespective of it to be Sedzeff or Hoffman, always double bond goes in conjugation with pH. If this X was fluorine, then also this would have been an answer. If this X is chlorine, then also this would be the answer. Okay, this is quite rigid when your leaving group decides the Sedzeff Hoffman. Okay, in case of bulky base, no issue. Then the answers remain towards CH3. Till here it is okay. So this was preparation of alkenes by elimination reactions. If I want to prepare alkenes by partial hydrogenation reactions, then I have two choices. One is palladium poisoned by barium sulfate or sulfur or quinoline or CaCO3 plus hydrogen. Okay, this is a syn addition reaction, and this thing is called Lindlar's reagent. Syn addition, so compulsorily always cis alkenes are formed. Now here we are doing just opposite of what we have done in raninical. In case of raninical, we increase the surface area of the reactant of the catalyst so that the activation of the catalyst is increased, it works better. Okay, but here we are doing just opposite. We are decreasing. We are decreasing the surface area of our catalyst, thereby making it less efficient towards hydrogenation reaction, and it goes only till alkenes and it stops further. Is it okay? So by using the same metal hydrogen type combination but a poison catalyst used, so answers stop to cis alkenes. If we want to make transalkene, we use sodium in liquid ammonia. This is called Birch reduction. And answers are transalkenes. Okay, the answers are transalkene when we use sodium in liquid ammonia. If we are said RC triple bond Cr in presence of sodium in liquid ammonia, then answers are this. Detailed mechanism, if we would have time some other day, we'll definitely discuss it. But still, a slight introduction is a must. Sodium in liquid ammonia will release electron like this, blue color solution. These electrons, when add to alkyne, then it form a radical anion. See, one side I can say anion, and on the positive I have added one electron. So radical anion intermediate is formed. Radical anion. Now we have already discussed that these electrons need to be far apart. So this always prefer trans geometry. Okay, instead of syn geometry. Now ammonia gives H to alkene. So H comes. As rotations are restricted, so positions remain same. Once again electron is added, minus charge is there, and now you add ammonia, RCH double bond CH and R. Transalkenes are formed. Okay, but remember, Birch fails for terminal terminal alkenes. Why? Because in case of terminal alkenes, it forms sodium salts rather than reduction. Okay, so it fails for terminal alkenes. It fails for alkene to alkane reduction also, because then this type of less repulsive geometry for the transit for the intermediate will not be possible. So it fails for alkene to alkane reduction also. Is that okay? So here we come to closure of our today's lecture. We have prepared alkenes by different methods, and let me tell you, this particular method, this particular point, that elimination reactions by itself is important for other functional group studies also. Okay, when we'll study alkyl halide chapter, it is very important that we need to know how it works. So please go through the overall elimination reactions. Okay, and if you have any problem, as I always say, do ask us. Is it okay? Whenever you have any problem, you can post on our Facebook page. You can ask us over there, and I like to solve that from those sites. Okay, till then, I would like to